let's continue on from where we left off in the last lecture. We were speaking about minimum spanning trees. And we're going to take a look at the greedy property of minimum spanning trees today in a little bit more detail, and try to see how it fits in with our algorithm is. And then take a look at how that greedy property is utilized in two algorithms, both of which use the greedy property, Prim's algorithm and Kruskal algorithm. So just a quick review of the last lecture. We spoke about the two types of optimization problems, two types of algorithms, broadly speaking, the greedy and the dynamic programming. And both of them have some. And so one of them was the optimal, which we'll take a look at in more detail today as far as the minimum spanning tree is concerned. The issue of overlapping subproblems was more relevant to dynamic programming. And we had some review of definitions of tree versus rooted versus a free tree, and an induced subgraph. And some of these concepts will be. And we looked at the general definition of a minimum spanning, where we graph and at what a minimum spanning tree would be, and if we could use our intuition with an this particular graph, and we saw that we could do it if it's a relatively small graph, and we use some intuition parts over. And so we'll see how that intuition feeds into the greedy algorithm and to the two looking at today, the Prims and Kruskal. So the first question is, look at the optimal substructure, spanning tree. Can somebody, based on in the last lecture, what is optimal substructure? And we showed that in a different problem, which was the shortest path as opposed to the minimum spanning tree. So we saw that in these the shortest path problem. So the question is, can we apply that to the minimum spanning tree problem? And can anybody think of a way how you could apply applicable in the minimum spanning tree problem? It should be because everything has to be the case. Look at the problem and say, well, does it have an optimal substructure? And can anybody see the optimal substructure in the minimum spanning tree? So remember what an optimal substructure was, and we saw that in the case shortest path. So this was, and to remind you what the optimal substructure was, basically a sum of the paths, and we're basically saying that any subroute is. So if the overall path is optimal, then any substructure which is within that optimal route is also optimal. Okay, so that's what an optimal substructure means. So think and see an optimal substructure here or not. Yes. Okay, so say that if I look at any substructure, can you point out any substructure which you'd like to start with? Okay, so let's take a look at A, B, C, and D, all right? And so that if you do the graph and you just look at A, B, C, and D, then the question is, if you think of the MST that was the overall, it's called that T, is shown in the original tan color. Internet is again happening today, but we'll have to just live with that. A sub, and let's call that G prime, okay, or let's call that G1, all right? And this was the original graph, and the original graph had T as a minimum spanning tree. And let's say this minimum spanning tree that we left off with as part of spanning tree, we'll call 1, all right? So is T1 a minimum spanning tree of G1? Okay, you can see that that is true, but is that always guaranteed? Yes. Okay, so let's take a look at, get your name again, Harrison? Yeah, so let's take a look at Harrison's suggestion that you're saying that let's form this as a sub, and your issue is that if we look at the spanning tree, or of calling the original one, let's call this as T1. So now, is this a minimum spanning tree as part of the original one? Is that your question? Okay. So if you think about the optimal substructure, it says that if you take any part of the original T, okay, and then apply the graph, then that should be an MST of that. Okay. Now, what you've done is you've a part which does any portion of T. Okay. So essentially, this structure of the original T. Okay, so you have to take a substructure of the MST and see if that is an MST of that part of the graph. Okay, so you can't take C and D because it's not a substructure of T. Do you get my point? So we would have, in order to be able to think about optimal substructure, we have to take T, okay? And a substructure of T could be A and C, all right? It could be A and B, it could be B or D, it could be any part of T, all right? So Jane's formulation was, let's take this part, okay, which has edges which form part of, okay, but we could take any other part and or not. All right, so I hope that clarifies that issue. We're going to take a substructure of T and see whether you know, that continues to be an MST of that particular substructure. All right, so you can sort of intuitively seems to be true as far as, you know, if you take any particular substructure, and hopefully you can see that that is in fact an MST. But then you have to do it more, right? But just to get your intuition running. So here's a proof, okay? What is generally referred to as a cut and paste proof, okay? So what we're going to do is we're going to say this is the original T, okay, which was in, right, showed you the original T, which was right up here. Okay, so this was the shaded tan was the original T, and we're going to cut out any from T. Okay, so this particular edge, which is part of the original T has now been cut out. Okay. I don't know what's happening on the internet side. Can people online hear me? Can somebody give me or a text queue if things are okay? So it's all right, not too bad. So we're going to remove any edge. It could be any edge, all right, within T. But we'll take U and V over here. And that because that is a tree, so it's going to partition the tree. Okay, it's going to convert the original into two partitions, and we're going to call them T1 and T2. Okay, so I'm going to portion T1 and this portion T2. Okay. And then we're going to use the concept that we talked about earlier of inducing a graph. Okay. So T1 and T2 are going to comprise of vertices and edges. So we're going to use the set of vertices that comprise of, let's say, T1, and we're going to induce the graph that corresponds to those vertices. Okay. So, so we're going to essentially call this G1, and we call this G2. So G1 is the sub-original, which is induced by the vertex in T1. Okay, so these are the vertices in T1. Okay, and those vertices produce a graph, which simply means it's going to connect all the edges and it's going to leave out the edges which are connected, which are going outside set of vertices. Okay, so this is the induced graph for T1, and this is the induced graph for T2. And so the theorem is that basically T1 is an MST T1, and similarly for T2. Okay. So now how? Okay, and the proof, as I said, is going to be that is generally used for such kind of proofs. Talking about graphs is referred to as, okay. So the original theorem, and now any thoughts? Any have any wild thoughts as to how one might prove this? You know, the hint is that it's a cut and paste. You know, so some portion of the and see whether you can come up with a proof by contradiction. Yes. So direct connection between what? Between the separated graphs or the original? Okay, so within each subgraph, you're saying that clearly it is a tree. Those are connected. Okay, and then keep on going with your thought. So the idea is that you've got two separate connected trees. You do have a forest now. You have removed one of the edges, okay, which was part of the original spanning tree. And what you're now trying to prove is that this this particular tree, which was part of the original, also a minimum spanning tree. Okay, so the question is, can you have another, let's say we redraw this and you have these 4 nodes, and let's say that here is a spanning tree, T1 prime. Okay, so this is the original T1, which was part of T, and now we're forming an alternative T1 prime. Okay, and we're saying, well, maybe T1 prime is actually the real MST and T1 isn't. Okay, so how do I that it's not possible prime with a lower cost, because remember the minimum spanning tree, a tree which has cost. Okay, some of it be smaller. So can you somehow show that if you form another tree within that induced graph, then it cannot have a lower weight, a lower cost? Yes. Okay, excellent. So what you could do is you could take and you could paste it into the original graph, and you add the original UV edge that we had. You put that back in. What you're saying is that this particular is the same. So you have the T2 over, okay, this edge that you've put back in, and you have T1 prime, which is a lower cost than T1, okay, has a lower cost than T1. And now we have this contradiction, this new spanning tree, which we can call T prime, okay, as opposed to T. This T prime, which is essentially T2 plus UV prime, and now T prime is actually has a lower cost to T, right? If this T1 prime had a low, okay, and so essentially you've come up with a very good proof by contradiction, okay, and that's essentially what the cut in process goes. Did somebody else have a response? I saw somebody else's hand is raised. No, okay, but does everybody? I'm memory. My short-term memory is really name Harrison. So Harrison's solution is a cut and paste solution. Can everybody see that? And I'm going to show it in the next slide, but let's just think about that. Does that work? You know, so you've come up with a T1 prime, which is saying, well, hypothetically, let's assume that that has a lower cost. All is connected up with the original edge, which we had removed, to the original, the rest of the tree, which was T2. And now it should have a lower cost as compared to the original T. T1 prime is less than T1, and the rest of it is the same. Okay, so forward proof by contradiction, exactly what I've shown over here. Okay, so and I'm saying that what if we had another T1 prime, which was had a lower cost? Okay, then all you take this T1 prime back into the original minimum spanning tree. Well, not the entire thing, but it's T2, and And so now you have an overall which is T prime, and that should be of a lower weight than T. And that would be a contradiction. So essentially, proof by contradiction, or you can say a cut and paste proof mechanism, has been used to be able to visually show that to you. This is considered a formal proof. So the slide in the shortest short is also does have an optimal substructure. And so this optimal substructure will become important as we go forward and the algorithm. Now the next thing is, and sort of similar, different, is the greedy choice property. Okay, so what does the greedy choice indicate? So we did go over the concept of a greedy choice, which basically says that we look for a local solution. And hopefully the local optimal solution will also be a globally optimal. And remember, I rough show you that if you have a terrain and you're trying to get to the top of the highest mountain you're over here, then a local solution would, in some cases, not be globally optimal. Okay, a local optimal solution over here would simply point you in that direction, and that would be globally optimal. But that is not necessarily the case if you're looking at a terrain and you're looking for optimal solutions. But if you do have an algorithm or a category of problem which does have the greedy choice, then basically what it says is that if you use a locally optimal solution, then in fact it will also be globally optimal. Okay, and so what could be the greedy choice property for the MST? Okay, so now essentially what we're saying is that we're trying to find some property which seems to be locally optimal, and that would hopefully also be a globally optimal solution. So if you think about what, if you're trying to find, and if you're a particular vertex, right? Let's say you're A or C or B, what would be a locally optimal solution for a minimum spanning tree? If you try to think from the point of view of a particular vertex, okay? And if you're trying to find a locally optimal solution, so if you think of a locally optimal solution, if you're doing mountain climbing and you on this particular edge of the mountain, then if you try to get to the top of the mountain, then clearly you want to go in the direction that is going upwards, right? That's called a locally optimal solution. Okay, but unfortunately in this case, as I said, it's not going to be globally optimal because you're going to be going in the wrong direction. You're going to a local peak. But if you think about the minimum spanning tree, can you think of a locally optimal solution? What would be a locally optimal solution? Just looking at A. This sort of links in to where Jane started off, right? So in the last lecture, I asked you, how did you come up with the MST, which happened to be correct, right? And you said, well, can you repeat that for us? Fortunately, you're still here. You're here today. You sure? The least cost edge. So you looked at sort of all the edges of A, right? All the adjacencies, and you said, well, which one is the least cost, right? And you said, well, let's start off with that. And you initially said, well, let's connect A and C because of these three edges. This was the least cost. All right, so compare 10 and 30 and 3. And so Jane picked 3 because it seemed to be a locally optimal solution. All right. But then you had this problem that you picked 10, and that didn't seem to be a locally optimal solution. All right, so if you think about from B's perspective, the locally optimal solution would be what? Would be would be 5, right? Because 5 is clearly smaller than 21 and 10. Okay, and so, but you didn't pick 5 initially, you picked 10, and that's because you were thinking, you had the big picture in front of you. But let's see if the locally optimal solution can be shown to be optimal as well. Okay, so we're going to say, well, this is the greedy choice. The greedy choice basically says that we're going to look at a particular edge, okay, and we're going to pick the edge which has the least cost. And what would be sort of combining that with an optimal substructure? Okay, how would we combine that? So, so how would we phrase that? Can you phrase the greedy choice in terms of an optimal substructure now? Okay, so bring both of those two together. So essentially, we're saying that we're going to pick for every node, for every vertex, we're going to pick an edge, which is least cost. Okay, and for A, we picked 3. For B, we picked 5. Okay, now can you see something happening over there, right? And can you form, a greedy property, and that you could prove? Yes, Thomas. Yeah, yeah, that's great. But how would that fit in with the optimal substructure? So let's look at B, right? For A, it was clear that 3 was the edge. Now for B, you picked 5. Now, how do we see that working out? Because 5 is, but 10 is also there, right? So how do you, how can you make a statement out of the fact that you have both 5 and 10? But what can you say about the least cost edge? Can we say something about the least cost edge? Yes, Harrison. Okay, very good. And initially you said that if you pick the least cost edge, then that is guaranteed to be part of the spanning tree of the MST. Is that what you also said? So if you picked any least cost edge for any vertex, can we see that if that's true, is it always part of the MST? Yes. As long as it doesn't make a cycle. So I'm going to rephrase that. So I'm going to pick any particular vertex, and I'm just going to look at an individual vertex, okay? So I'm picking a vertex, and I'm looking at the edges, its adjacency list, okay? So we're not really talking about cycles yet. We're just saying, and presumably it's not connecting to itself, okay? So let's disregard that particular case where it's actually going to itself. But assuming that you don't have any vertices coming, edges coming back to yourself, then if you look at all the vertices that are going out of that particular, all the edges which are going out of that particular vertex, and if you pick the least cost edge, then we're saying that that is guaranteed to be part of the overall MST. So we look at the edges coming out of E, for example, vertex E. We have 24, 15, 16, and 1. And 1 is found to be the least cost. And so we can see that 1 is in fact part of the MST. Okay. If we take a look at any other vertex, then 22 to 16 and 25, this is the least cost edge. And that is, we can see that that is part of the MST. Okay. In some cases, you will have more than one. Let me make it a little cleaner. So in some cases, you're going to have more than one edge, which is part of the MST. But what we're saying is that the least cost edge is guaranteed to be part of the MST. Okay, so we're not making a statement about 15 here. We're just making a statement about the least cost edge, and we're saying that is going to be part of the MST. Okay, so in a sense, the greedy choice can be rephrased as, you know, if you pick the edge, which is the least cost, then that will be part of the MST. Okay, so and then we can expand on that concept. Yeah. So that's what we're going to expand now. All right, so we're starting off with just one vertex. Okay, and then we can see how we can expand that. All right, so here is a more, you know, as you said, that was initially just one node, but now we're going to expand that concept, and we're going to say the following. All right, so we're starting off again with an original T and a graph G with a bunch of vertices and edges. And now what we're saying is that let X be any subset of V. Okay, so originally I was just restricting myself X to be a single vertex, but now I'm saying that X could actually be any bunch of vertices, which is a subset of the original graph. So in this case, I've picked just one vertex, but in this case, I've picked 3 vertices. Okay, and we're saying that if you take any subset X of V, all right, and we let any edge UV be the least weight edge that connects X to V minus X. Okay, so essentially what we're doing is we're cutting the graph into 2 parts, into 2 disjoint parts. Okay, in this case we cut it along over here. Okay, in this case we're cutting it along over here. Okay, and we're saying that along this particular cut, if you picked the least weight edge, okay, so the least weight edge over here was 3. Okay, but now if you take a look at a larger set of vertices X, which is A, B, and C, and you looked at the cut which is connecting it to the rest of the graph, which is V minus X. Okay, so this is V minus X, this is X, and so if you look at the cut over here, then we're saying that here now the following edges which are crossing that cut. Okay, what are those edges? Well, it's now 24, 5, 30, 20, and 22. Okay, can you see that? Edges over here. Okay, these are the points where X and V minus X, there are edges which are interconnecting these. Okay, and now what we're saying is that if you pick the least cost of those edges, okay, if you pick that the one which has the least weight, then that is going to be part, that particular edge is guaranteed to be part of the minimum spanning tree T. Okay, in this case, if you look at it, you can see that out of 24, 5, 21, 20, and 22, 5 is the least weight edge. Okay, and now let's take a look at other random cuts. Okay, so let's take a look at the original graph, which is a bit easier to pick. So now we've expanded our greedy choice, and we're saying that we're going to have X not only be a single vertex, but it could be any subset. Okay, now pick any subset and form that cut. And I'd like you to explore that. Yeah. Sorry? E, D, and F. Okay. So here's a tricky one. So let X be these edges. Okay. And now we're saying, and V minus X is everything outside. And it's now in two parts. Okay. And now we're saying that we pick what are the set of edges which are connecting X to V minus X? Can you point this out? So it's 24, 5, 30, 20, 22, 25, and 1, right? So those are the edges which are cutting across V minus X and X, okay? And now what we're saying is that if you look at the least cost, the least cost edge, which is in this case happens to be 1, then that is guaranteed to be part of the tree of the original minimum spanning tree. That's guaranteed to be part of the U comma V is now guaranteed to be part of the this is U here and this is V, and we're saying this particular edge is guaranteed to be part of the tree of the MST. Okay, I mean, think about any other cuts. So let me remove this, and somebody else want to explore that cut. Take any other cut and see if that is true. Anybody else want to pick a cut? Pick a cut, pick any cut. All right, take your pick. So it could be any subset of vertices. Anybody else? Which you think may not satisfy the condition. So let me just pick a random bunch of cuts. Okay, so I take a look at this. All right, so 3 over here. Okay, I take this cut over here, and it has 3 and 5, all of those. So 3 is again in it. All right, I pick this, 5 is over here. I pick this cut, 2 is there. Okay, so I mean, you could cut it any way you like, and you'll find that the least cost edge in that particular cut is always guaranteed to be, is always going to be part of the minimum spanning tree. Okay, so that's a very interesting greedy choice property of the minimum spanning tree problem. Okay, now the question is, how does one prove that? How would we prove that? So we just did a proof, a different proof, all right, which was the optimal substructure. And we used, a technique called cut and paste. So can somebody think of a proof for this, which could also be along the lines of maybe cut and paste, okay, which you could categorize it as a cut and paste operation. Notice that my camera's gone all over the place. Okay. So can somebody come up with a proof just like Harrison had for the optimal substructure for the greedy choice? And we prove the greedy choice is in fact true. Okay. Tricky. Yes, Thomas. Okay, but can you put that in, sort of try to depict that pictorially in this graph? Sounds right what you just said, but I need to be able to follow that, and maybe the rest of us as well. So say that again, and let's see if we can give an example of that. So I just want you to repeat your proof. but I want to pick a real example from that graph and see if we can, illustrate your proof. Okay, so let me just draw it over here. So A, B, and C, all right? Yeah. Okay. And we're drawing a cut, right? So we are cutting those. So this is X and this is V minus X. And so here is a cut. Yeah, okay. And we do have some edges crossing over, right? So we have 3 of these edges over here, which are cutting the cross, and 1 over here. So we do have 1, 2, 3, 4, and 5. So we have 5 edges which are cutting across, okay? And currently this is our least cost edge, which is 5. Okay, now continue from there. Mm-hmm. So let's assume that we took another edge, okay, this particular edge over here, which was not the least cost edge, right? That's what you're saying. And we connected these two. And we said, well, somehow now we need to show a contradiction. Okay, then now you can come up with a new MST, which is perhaps lower in cost. Yeah, so you're almost there. I think you said it, but let's just go through this. So now, how do we actually show that if you picked another edge, which was not the least cost edge, let's say this had a cost of 22, but let's pick something closer. Let's assume that this had a, well, let's just stick with it, 22. So this has an edge of a weight of 22, okay? And so if we picked that particular edge, and then keep going, we have to do some cut and paste. Yeah. So what we're saying is that now we remove this particular edge and we create a new spanning tree, let's say T prime, which comprises of the original trees, excluding 5, but now including 22. And we're trying to say that that is going to be of higher weight. Yeah, and that the original tree would have been of a lower cost. And so we, yeah, so can you just complete that part? And why would that be true? Why would it be of a higher weight? We're almost there. So we've picked, instead of 5, we've replaced that with 22, okay, which has a higher cost. And now we're constructing a new tree, okay, with 5 replaced by 22. And now we're saying that that couldn't be the least cost minimum spanning tree because this particular edge has a higher weight, okay? And so the new cost would be this plus this portion, and you can see the contradiction, okay? So very good. We're going to do this in a slightly different way. Okay. So here is the cut and paste. It's almost the same. Okay, but slightly different in how it ends. So we'll say, well, let's assume that this was the original minimum spanning tree T. Okay, and we let UV be the least weight edge. Okay, that connects X to V minus X. So this is V minus X, and you have X is the example 2 case. Okay, and this was the original minimum's least weight edge. All right, and now we say, well, let T prime be an alternate MST. So now let T prime over here be an alternate MST that does not contain UV, that does not contain 5. Exactly what your suggestion was. Okay, so we've cut this out, this particular edge out, and now we're saying, well, consider path from U to V. Okay, now we have T prime, so that's a connected tree. Okay, so every edge, every 2 vertices should be connected. So let's take a look at U and V, which were part of the original edge, which was taken out. And now let's trace a path through T prime, which connects U and V. Okay, now what would that path be? That would be, in this particular case, this particular path. Okay, that's how we can get from U to V. Okay, and now what we're going to do is we're going to swap U comma V in T prime. Okay, with the first edge that happens to be over here is shown here as A and B on the path that connects a vertex in X to a vertex in V minus X. Okay, it's essentially saying pretty much the same thing, but it's putting it in a bit more formal manner. So you only end up with one particular edge. So earlier we had picked a particular edge at random. Okay, but now what we're saying is we're going to pick a particular edge which is part of the path from U to V, and it's going to be a simple path. Remember, between every 2 vertices in a tree, there's going to be only one path, and that's referred to as a simple path. Okay, because a tree by definition doesn't have any cycles. So now we've taken this particular path which connects U and V, and we found the edge which goes from X to V minus X, which is this particular one. Okay, so it's the first edge which connects X to V minus X. All right, and now what we'll simply do is we're going to replace, we're going to swap U comma UV in T prime with this particular. So we're going to replace 22, and we're going to replace it with this particular edge of this. So swap UV in T prime with the first edge on the path that connects this. Okay. So sorry, let me say that again. So instead of the T prime now comprising of this particular path, we're going to replace this with 5. Okay. So we've taken T prime, which was following a different path. We found the edge between U and V, which was the first edge which was crossing over from X to V minus X. We've taken that particular edge, we've cut it out of T prime, and now we've put in the edge UV in T prime. Okay. And so because this particular edge is a least cost edge, okay, and presumably this is of a higher cost, so now T prime will have a lower weight. Okay. So the rest of the T prime remains the same, and you've essentially found a contradiction. Yes. So the first edge is essentially, now we're taking the path. Let me draw that again. So we've got UV, okay, and we're saying that there is only one simple path between U and V on T prime. Okay, T prime is the is the alternate MST. Okay, and so there must be some point where U and V cross over. Okay, so this is the path that is connecting U and V on T prime, and this is the first edge. Well, in this case, there's only one edge. Okay, and so this is the edge where you cross over from X to V minus X. Okay, and so in T prime, we simply replace, you cut this out and you replace it with these two. Okay, replace it with here. Sorry? So T prime is a minimum spanning tree, right? So would that be true if it's a forest? That's a good question. So that goes back to your original thought. I think the example that you had come up with, where you had picked D, E, and F. All right, so let's try to see if that works out. So you're taking D, E, and F. Okay, and you're cutting out the least cost edge. So that would be a little different example. It kind of get confusing, but you're going to cut this out. And so this would be U, and this would be V. Okay, and so presumably the first edge would be, and the path between U and V would be this particular path. Okay, and this is the edge which would be replacing with this edge. Does that make sense? Okay, so you can sort of look at this proof, and it's a cut and paste proof, as we say. Okay, and if you don't completely follow it, just come up with your own examples. As Harrison just pointed out, you can think of different examples and see if you can prove it in a general way. Okay, and you should be able to come up with a contradiction. So that proves the greedy choice property of the minimum spanning tree. Okay, so we've proven two theorems, you might say. One was the optimal substructure, and then the greedy choice property of the MST. Okay. So now let's see how we can apply it to a couple of algorithms, and we'll first take a look at an algorithm. We'll take a look at Prim's algorithm, which is actually supposed to be superior to Kruskal's algorithm. So we'll take a look at that, and then time permitting, we'll take a look at Kruskal's algorithm as well. Okay. So Prim's algorithm is fairly, it draws directly from our greedy choice. Okay, so it's sort of expanding on the greedy choice property that we just saw. So it starts off by as follows. So you're going to build a minimum spanning tree, and we'll call that A. All right, and let's assume that we have this graph G, and it has a set of weights W, and the minimum spanning tree is going to start off at one particular root. Okay, so we're going to select a particular root, and we're going to apply the MST on that particular root. Okay, so let's say that we picked the root to be A over here. Okay, and so we've got an arbitrary root. Okay, and what we're going to do is we'll maintain a priority queue, which comprises of the rest of the vertices. Okay, V minus A. So we start off with essentially maintaining a priority queue, all right, which comprises of everything in the entire tree, in the entire graph. Okay, so initially we're going to assume that our MST, of course, we're going to slowly grow it. Okay, so initially our minimum spanning tree is a null tree, all right, and V minus A is essentially V. Okay, and so I've shown V minus A as the blue dotted area, and A is the null part of the graph. Okay, and essentially we're going to slowly expand A so that it becomes a minimum spanning graph. Okay, And V minus A is going to be maintained as a priority queue, as a minimum priority queue. Okay, what does that mean? It means that basically for every vertex in V minus A, we're going to assign a key. Okay, and that particular key is going to be the minimum weight edge of any vertex which connects V minus A to A. Okay, so think about this. I'm going to have a key, and I've shown the key over here in yellow highlight. Okay, so these are all the keys, and we're going to initialize all the keys to be infinity. Okay, except for the root key. So the root key, the root in this case is A, and so the root key is set to be 0. Every other key is set to be infinity. All right, and so V minus A is going to be a minimum priority queue, which is going to be based on the key value of every vertex. Okay, so when you start off, clearly the minimum value is going to correspond to the vertex A. Okay, because this has the least value, least key. We're also going to start off by we're going to maintain the parents of every vertex. Okay, and essentially that's how the set A is going to be maintained. It's not going to be explicitly maintained, but it's going to be implicitly maintained. Okay, it's going to be implicit in the sense that for every vertex there's going to be a parent. Okay, and that's how we're going to figure out what the minimum spanning tree is. Okay. So so far so good. If you look at the initialization, so let me just make sure that we understand the initial part of this tree. We've completed lines 1 through 7. So what we've done is we've initialized all the keys to be infinity. We have initialized all the parents to be nil. We've set the key for the root to be 0. We initialize Q to be 0 initially. Okay, the null set. And then for every vertex U in V, we're going to simply insert that into a priority queue. Okay, so you can imagine that it's a heap, and that heap is being maintained, and all of these values are infinity, and so on. And the only value which is minimum is going to correspond to the vertex A, which will have a key of 0. Okay, and that's going to be right at the top of the heap simply because it's a min heap. Okay, so far so good as far as the initialization of the minimum spanning tree algorithm. Okay, now once we're done with initialization, now based on the greedy choice, how do you think we're going to expand? Let's just build up on that. So we've initialized this. How should we expand this? Yes. So we're going to look, so which weights are we going to look at? The minimum weight of what? So we've started off with a root, okay, to its adjacent nodes, adjacent vertices. So what we should do is we should look at the adjacencies of the root node, okay, and then we should look at 4 and 8, which are the two adjacent vertices, which are the adjacencies of A, and then we should look at the least cost edge, okay, and then we should expand this particular the A portion should sort of expand in the direction of the least cost edge, okay. And so if we do that, we should come up with this. And then what would be the next step? So you're going right, just keep on doing. What would we do next? Okay, so that's right, but we're looking at the adjacent edges of what? Of B, of A, or of what? Okay, so we should look at the adjacent vertices of B, okay, which is the node that you have suggested should be added next. And then we should look at the least cost edge of that, okay? In that particular case, it should actually be 4 again. So, but 4 is already there. So we need to exclude that, okay? And if you look at the one which is not already in A, which is going to be 8 over here, okay? And now we should include that in the tree that we're building up, okay? So that's the general idea. It seems fairly straightforward, right? But it's a little tricky when you actually try to implement it as an algorithm. So let's take a look at how we're going to do it. So here's the rest of the algorithm from lines 8 to 14. We're going to continue doing this until the queue it becomes empty, okay? And Q, remember, is the set of vertices outside of A. So as A is going to become bigger and bigger, V minus A is going to eventually contract, and V minus A is eventually going to become a null. Okay. So we're going to stop when the priority queue becomes null. Okay. We've already inserted the root, so we're going to extract the root out of it. Okay. And that's going to be an extract min operation on a heap. And extract min simply takes the minimum value in the min heap, okay? And it also removes that from the heap, okay? So not only are we getting the minimum value, but we're also removing that. So what does that imply? What's the complexity of that operation? Sorry, log n. Why? Because we have to reheapify. Okay, so we've taken the top part of the heap, and so now we've got to apply the bubble down operation or something like that. Bubble something. Okay, we've got to maintain the heap, and then the next thing we do is for each vertex in the adjacency of U, which is exactly what you had suggested, right? So we look at the adjacent vertices of U. Okay, so now U is so before that, so we still at A, we're looking at the adjacent vertices, the adjacencies of A. We're going to make the adjacent vertex parent to be yourself, okay? So V dot pi is going to become U, so the parent of B is going to become A, the parent of H is going to become A. And then we're going to change the value of the key. So the key value over here is going to become 4 from infinity, okay? And that's going to happen only in the following cases. So we want to exclude any vertices which are already which are not part of the queue, okay? So you don't want to look at this particular vertex. Well, in this case, that's not applicable, but in the next case, you'll see that. So we'll update 4 and 8, which is essentially saying that the key value is going to become the weight of the edge, okay? So 4 comes out from here, 8 becomes the new key value of H, 4 becomes the new key value of B, okay? And then what we're going to do is we're going to apply the decrease key operation on that particular heap, and which basically says that we're going to change the value of that particular key. So each one of them is the key values are going to change, okay? So you remember how that happens in a heap? So if you have a heap and you take a particular value inside and you change its priority, what's going to happen? Yeah, you're going to either bubble up or bubble down depending on the value. And so this is a decrease key. So essentially what we're saying is that it's going to bubble up, right? Because now we're reducing the value of that particular key, okay? So instead of having the key to be originally something else, which could have been infinity, we're now going to change it to be a 4, and so it's probably going to bubble up, okay? So that's the decrease key, and this again is going to have the complexity is going to be log of n, all right? So so let's do that. So we've got these as the new keys, and so now these have the heap has been reordered. And so we're going to repeat after we're done with this. We're going to again extract the minimum value from this particular heap. Okay. And now the heap comprises of all of these vertices. Okay. Actually, these are the vertices in the heap. Okay, v minus a. And we're going to look at the one which has the lowest value. So you can see that, well, 4 versus 8, if you compare all of these to the rest of the values which were infinity, I think this should have been, well, you can see that there might be a little typos in here, but you can see that you're going to be basically looking at 4 versus 8, and the rest of them, the keys are going to be infinity, and you're going to select 4. Why? Because it's going to be the minimum value in Q. Okay, and once you've extracted that, okay, you're going to look at the vertices from B. Okay, and now you're going to look at the vertices of the edges of B, which are in Q. Okay, so Q is now shown over here. So you're not going to look at this particular vertex because it is not in Q, and you're only going to look at the vertices 8 and 11. Okay, and then you're going to update their weights. Okay, so this weight is going to become updated to 8. Why is that? Because the original key value was infinity, and now you're going to compare it with the weight of this particular edge, u comma v. And if this weight 8 is less than infinity, then you're going to change the key value to be 8. Similarly, you're going to look at this particular key value, and you're going to say, well, is this particular edge has a lower value than the current key value, which is infinity. So if that is the case, you are going to update the key value. Okay, and you're going to do a decrease operation. So you're going to end up with 8 over here and 8 over here. Okay, so essentially, if some of you remember Dijkstra's algorithm, which we covered in 210, how is it similar or different to what we're doing right now? Does it remind you of Dijkstra's algorithm? And what we're doing in Dijkstra's, maybe way back when you took 210. Does anybody remember? We'll cover Dijkstra again a little further down the road, but just to remind ourselves. Yeah, exactly. So here, the only difference here is that the key is now going to be the weight. Okay, so the key over here is simply going to be the weight of this particular edge. It's not going to be cumulative cost of getting from A to C. In Dijkstra's algorithm, it would have been 8 plus 4. Okay, it would have included the cost of the earlier cost to get to B. Okay, so that's a small difference between Dijkstra's algorithm and Prim's algorithm. Okay, and we'll come to Dijkstra's algorithm. We'll see that as well. Okay, so let's take a quick look at the rest of the algorithm. You've got a basic idea. You've got a few minutes left, and you can now hopefully see through this. So this was the original cut. Okay, and we updated the keys for both of these adjacent edges, okay? And we picked the minimum of these two, and that is 4 compared to 8. And so we updated, so now this has been extracted from the Q, and now the Q comprises of everything on this side, and A comprises of everything on this side of this particular cut. Next, what we're going to do is we're going to look at the minimum value, the least cost edge across this particular cut. Okay, and so this cut is going to comprise of these edges 8, 11, and 8. And so we could pick either B, C, or AH edge. Okay, either one of them could have been picked up, but in the example that is from the book, they've picked this particular edge to be the next edge that is picked up. And so we're going to now update its neighbors, okay, with the cost of the edges. So this one becomes 7, okay, from infinity, this comes down to 7, change, and this goes down from infinity to 4, which is the cost of the edge. This goes down from infinity to 2, all right? And now we look at all the edges which are still part of the queue, which are I, F, and D. And you look at the one which has the least cost, which is clearly 2. Okay, we extract that from the heap, and so V minus X, V minus A becomes smaller. And similarly, now this is the new edge, and now we look at the least cost edge on all of these edges. And that happens to be, well, there are a couple of them. Well, no, actually there's only one, which is 4. And so you can see now, after this, where were we? We were at D. And so from here, we pick this particular edge. And now you can see that the cut is going all over the place, all right? But you can, if you just follow this, you can see that every time we're going to pick the least cost edge. We're going to include that over here. And finally, we're left with 9. And so eventually, you can see that your queue is going to become empty, and you're going to be left with is a minimum spanning tree. Okay. And so the idea was basically that you looked at, you chose the greedy property, which was essentially saying, looking at a local optimum. You picked the edges, which are the least cost, and then you expanded the tree.